Hello, and welcome back to a new video series. My name is Paul Zakella, and in this video we'll be discussing our second assignment for our Process Dynamics and Controls course. So I've gone ahead and drawn our situation up on the board. As you can see, we are given a tank, and we are given three different fluids coming in. They are of the same material, of course, but they are coming in at different temperatures and at different flow rates as well. And this is perfectly well mixed, and we are focusing on when it is going on after a very long time. And we are going to solve for the change in height, change in the concentration, and the change in temperature, all respective time. And we're going to go ahead and create a code for in our Python so that we can go ahead and work those out. So with that being said, let's go ahead and get started. Like I said, we want our change in height, CA, and temperature, right? We want to figure out what all three of those are. So, like usual, like we always do, we work out with finding the change in volume, right? So that we know that the change in volume with respect to time is simply equal to the flow rate coming in minus the flow rate coming out, right? Minus Q out. Perfect. And then we can work this out as what Q in is and what Q not is, or Q out is. Q in is simply the summation of these three flow rates coming in. So Q in is simply Q1 plus Q2 plus Q3, right? Simple. And for Q out, we will be using what we did in our previous set of videos. We worked out a energy balance between the top and the bottom. And if you remember, we worked out that the kinetic energy with the potential energy to find out that the V out is simply equal to the square root of 2GH, right? We can go ahead and plug that out for Q out, as it is simply that multiplied by the cross-sectional area of where the flow is coming out, which is AH. So we can rewrite this as Q out is simply equal to this times AH, right? Now something that will help us out later on is I'm going to rewrite this equation in favor of H, as we will be needing to plug that in a value into our Python code. Our initial value, if we rewrite this, we end up with Q out over AH squared all over 2G, right? Okay, so now we can go ahead and rewrite this. We know that volume is simply equal to the height multiplied by the area, and we know that our cross-sectional area here isn't changing, it is simply our height changing. So we can go ahead and rewrite this dV dt as simply dH dt multiplied by our cross-sectional area, which we're going to call AC. And that is roughly a meter squared. That doesn't matter for now, but that'll help us out later for our numbers. And that is simply equal to, like I said, the summation. We're going to say I from 1 to 3 of QI minus Q out. And we know that Q out is this value. And we can go ahead and rewrite this so that we get dH dt is simply equal to the summation of 1 to 3 of Qi minus Q out all over AC. Alright, that's our first expression for the change in height with temperature. So I'm going to go ahead and plug this in over here so that we can free up some space. Okay, so that is for our first one. Now we want to go find out the change in the concentration of A, right? Ca. So what we can do here is similar to what we did here, is simply multiply it by the concentration, right? Simple mass balance. If you work this out, you say that Ca multiplied by dV dt simply equal to the summation from I1 to 3 of qi ci minus q out ca. And I'm not calling this concentration that's coming out C out or anything else. I'm calling it Ca because Ca is equal to the concentration that's coming out because we are paying attention to this after a very long time. So that Ca equally balances out to be C out. So if we go ahead and rewrite this, we can pull this Ca to the right side so that we get dV dt is simply equal to that whole summation qi ci minus q out times ca all over ca. Right? Nice simple. Then from here, what we can go ahead and do is work out again our dV dt. I think we might need that ca actually. Sorry, I've done that a little bit too early. Let's see. So if we go ahead and multiply this out, we get AC multiplied by DH dt. So this was a little bit prematurely because we want to find out a change in concentration, right? So actually what I'm going to do is pull this AC to the right side, leave the CA here, so that we're ended up with, again, summation from I1 qi ci minus q out ca, we're all going to be divided by AC, right? Cross-sectional area. And now we can work this CADH dt out. And I'm going to do this over here. So CADH dt, if we work this out, we get CADH dt plus H CA dt. Alright, so I can go ahead plug this in over here so that we're ended up, I'm actually going to just put this on the left side and then bring this already to the right hand side so that we're left with H CA dt is equal to summation from 1 to 3 of qi ci minus q out ca all over AC. Like I said, we brought this over to the right hand side, so we're going to subtract minus ca dh dt. Of course, we're not over, we still have this h on this left hand side, so I can go ahead, pull this out, and divide this whole thing by h. Alright, so there is our equation for the change in CA. I don't know why I forgot to put the D there. Apologize. But there is our expression for the change in CA. So I'm going to go ahead and write this here, free up some space, and work out on our final expression for temperature. So we said one qi ci minus, erasing this out a little bit, minus q out times ca, then divided by that whole thing by AC, and then minus, divide this whole thing by H. Alright, we have some space now. That should be enough for now. So let's go ahead and get started. Last expression, change in temperature. So we're going to go ahead and do what we did similar to up here for the change in concentration. We're again going to start off with the change volume with respect to the time, but we're going to multiply it by temperature, of course, but also by density rho and the specific heating capacity Cp. Right? We're going to multiply those values throughout the whole expression so that we're ended up with the right hand side being equal to the summation of I from 1 to 3 of Qi, then we have Ti rho Cp minus Q out T rho Cp, right? Then what we can do here, nice and simple, we can multiply out all of these rho CP's, right? We don't need these, so this becomes dV dt is equal to that. And of course, we're going to have to change this dV, so I'm going to go ahead and do that already to our AC times dH. So we're going to have, back to purple, we're going to have AC dH dt multiplied by T is equal to the summation from 1 to 3 Qi Ti minus Q out T. Nice and simple, right? So now go ahead, bring out this AC on this side. Then multiply out this dHT over dt. Put that over here. dHT over dt becomes T multiplied by dH dt plus H dt dt. Alright, so now we can go ahead and plug that expression over here on this left hand side. So that we're up with dH TDH dt plus H dt dt is equal to that summation of Qi Ti minus Q out T all over AC. Right? Then again, we can go ahead and bring this expression to the right hand side. So then we're going to have minus T dH dt. Right? And finally, to get our expression by itself, dt dt, we're just going to divide that whole expression again by h. So this, that whole thing is going to be divided by h for a new expression. I'm going to go ahead and rewrite this really quickly here. Summation 1 to 3 of Qi Ti minus Q out T. And then we're subtracting T multiplied by dH dt from it, and then that whole thing divided by H. Alright, so there we have it. There are our three expressions that we'll be using, our change in height, concentration, and temperature. So now we can go ahead and write this up in our Python code and solve for those three numbers. Hello, and welcome back to Collaboratory. Gone ahead and already put in these basic functions that we've used many previous times. So let's go ahead and get started. What else we know? We can go ahead and plug in our givens or known equations. So we know that Qn naught, we're going to have given values. Same for Ca and naught. Right? And then the same with temperature. And these are all going to be arrays, right? And for the flow, we have 0.5, 0.3, and 0.6. 0.6 respectively. And for the initial concentration, we have 0, 1, and 0.5. And finally, for the temperatures, we are given 80, 65, and 90. 80, 65, and 90. Right. That's not it. We also know our cross-sectional area, AC. We know that's 1 meter squared, as well as our A hole. The hole that's coming out is 0.1 meters squared. Of course, we also know gravity, right? 9.81 meters per second squared. Okay, sweet. So now we can go ahead and create an equation so that we can go ahead and solve for those three things. So we call define, we call it right hand side, right? And then we're going to be passing temperature, and then of course a vector as always. We're going to have to unpack it, and then our values have QN, CA, N, and TN. Right? And then we're going to pass through the vector. We're going to have our height, right? What else? Our concentration and our temperature as well. Right? And now we can go ahead, now that we've unpacked this, we can go ahead and put in our equations that we achieved earlier, right? So I'm going to start off with our Q out. Right? So that is simply equal to AH multiplied by square root of 2GH. So NP dot square root of 2 times G times H. And that whole thing multiplied together gives our value for Q out. So from there we can go ahead and write our values for dH dt, for dCA dt, and what just happened? dCA dt and dt dt, right? With that said, let's go get started. dH dt, we said that is the NP sum of Qn minus Q out, right? And all that divided by AC. Right? And for dCA dt, a little bit more complicated. We have sum of Qn multiplied by concentration, Cn, or call that Ca, I think, right? And that subtracted by Q out Ca, Q out multiplied by Ca, right? P sum of that minus that. I don't think I need that extra one, but okay. NP sum that divided by that, and then divided by AC, right? Divided by AC, and then we will be subtracting CA multiplied by DH dt. Looks fairly right. Sum of Qn times Ca minus Q out Ca all over AC minus Ca. Okay, that looks good. Yes, so we can go ahead and continue on for dt dt. Actually, it's very similar to this past one, so I'm just going to copy and paste it for times purposes. But instead of this Ca, we're going to have temperature, right? That's the only thing that changes, if I'm correct. So we're going to have sum Qn T minus Q out T divided by AC minus T times dH dt. And that whole thing is then divided by h. Okay. So that should be good. And then of course we want it to spit out define result. Okay, wait, let's make sure this is all good. I don't know why I couldn't come back with that. Okay, return. We wanted to return array, right, of dh dt, dca dt, and dt dt, right? Okay, so now we can go ahead and solve this out. So what we want to do is we want to recall our root function. So I'm actually going to call this solution so we can go ahead and pull it back out after. And then of course we have to give our function, and what we're going to do is root lambda v, and this is going to help us kind of simplify down this problem a little bit. Of course, the right hand side, we're going to be using that expression, and then we're going to be using t v again, and then give our values for oops. Sorry about that. Okay, so right hand side, we're gonna give this values. For time, I'll just give it 0 vector, and then now we put in our values: q in not, ca in not, and t in not. Right. Then we have to give our initial guess, so that is where our value for h comes in. So we go create an array for that. We're gonna have q out over ah, so we have q out over ah is q out q out squared, or I think this is the sum. Okay, do the sum of q not divided by ah. Okay, wait. Array the sum. I think, yeah, I don't think we need an array actually, but sum of q n not divided by ah. Need another one. So divided by ah, then that is squared, and divided by 2g, 2 times g. Okay, I have one too many. So I have, okay, I need an extra one here then, I think. So I have NP sum that divided by AH, not squared. That whole thing is divided by 2g, the area of that, okay. And then, of course, we're going to have initial guess for CA and TN, which could give 0.5 and 70 for our initial guesses. Go ahead, issue. Simplify this down a little bit. So array of base AH2. This work? No. Oh, okay, I think I see what I did. Something like this, I think. I'll close this. Another one here. There we go. Okay, so I just these initial guesses weren't part of that array, so that was why we had an issue. So now if we do sol.x, we call Apollo, go ahead and get our values, which have an issue. These brackets are always okay, I think I noticed my mistake. Yes, DCAD I forgot to put a minus or divided by h at the bottom. So this whole thing is divided by h. Let's see if that does it. This might do it. Oh, okay, there we go. So I had a few mistakes in my equations up here. Too many paragraph or too many parentheses or too many brackets, and as well with here I messed up my estimations. But yeah, so this is what we end up with our given values of 0.5 and 70 for our initial concentration and temperature. We end up with these three values after a long time. The height is just under 10 meters, and the concentration is just under 0.5, and the temperature is just over 80 degrees Kelvin. So with that being said, there you have it. There is the working out for our first assignment of this video series. Thank you, and I'll see you in the next one.